geometer sketchpad. Okay, so if you were to take and draw in 3 angle bisectors, so here you can just kind of follow along on this. So if I took this angle right here and I constructed the bisector to it. Okay, so this represents that angle being bisected. If I do the same thing with a second angle and construct its bisector, the point where those intersect is going to be my incenter. Okay. Now, would I need to find this third angle bisector to know where that incenter falls? If I specifically tell you that incenter is where all the angle bisectors intersect, if I have 2 of them, I found that location. If I choose to do a third one, so if I were to bisect this angle as well, all that it really acts to do is it confirms that I had the right place. So here I can see that that angle bisector also happens to pass through, and so it's just a confirmation that this was in fact the incenter. And now, with respect to the incenter of a triangle, you can see here no matter where I move this around, that incenter is going to stay in the interior of my triangle. And there's one more thing that this incenter does, and what it does is if you connect or if you construct a perpendicular from the incenter to any of the sides, okay, so if I were to construct a perpendicular here, okay, so here from between those 2 segments right here, if I construct a line along that, giving this a perpendicular, okay, I can hide the markings here that I use for this. But this red line right here, that perpendicular segment from the incenter to the side, is going to be the radius of a circle. If I draw that circle from the incenter to that side, what you see here is it's going to intersect the triangle on each side. So again, no matter where I move this, that incenter remains the center of a circle that is inscribed within this triangle. And so that's the other property to keep in mind. Okay, and so when I look at this, the incenter also happens to be the center of an inscribed, or a center of a circle that's inscribed within the triangle. So what that means is when I construct a circle that's inscribed within here, this is the intersection of these angle bisectors. So I know that these 2 angles are equal, these 2 angles are equal, and these 2 angles are equal. Okay. I know that this perpendicular from the incenter to any side, or in fact all of the sides here, is a radius of that circle. Okay. And so those are the relationships that you need to be able to identify. All right, so if we take our triangle here and we construct a perpendicular bisector, what that means is we would first want to find all the midpoints of these sides. So if we find their midpoints, so that means that these 2 lengths are the same, these 2 lengths are the same, and these 2 lengths are the same. So there's our midpoints. Okay, and then we construct a perpendicular through that midpoint. So here's a perpendicular bisector. Again, it meets at a right angle. And if we take any other one, perpendicular through that point, where they intersect is going to be our circumcenter. Okay, so this right here is the point of intersection of all the perpendicular bisectors. Now once again, once you have 2 of them, you're good, but if you find the third one, that merely acts to verify that it is in fact the correct point, and we can see here that the third one also passes through that, which it should. Okay, so in this particular case, you see that the circumcenter falls outside, but it can also fall right on the triangle. It can also fall somewhere inside the triangle. And so it's really just a matter of, are we dealing with an obtuse, acute, or right triangle? If it's a right triangle, it falls directly on. If it's an obtuse angle, it falls outside. And if it's an acute triangle, it's going to fall in the interior. Okay. Regardless of where it falls, though, the relationships are equivalent. Oops. And that is this circumcenter is also the center of a circle. But this one is the center of a circle that when you draw it and you pass it through one vertex of the triangle, you're going to see that it passes through all the vertices as well. Okay. So the circumcenter is actually equidistant from every point on that triangle, or every vertex of the triangle. And so that's the relationship that you have for this when you're constructing perpendicular bisectors. Okay. So this gives you the center of a circle that's said to be circumscribed about the triangle. Okay. And it is the point that is equidistant from all three vertices of the triangle. Okay. And so where you would see this in sort of a word or applied problem is if you had three cities located in three different spots. If you constructed a triangle for those and a perpendicular bisector of each side of that triangle and found where that intersection is, that would give you the point that is equidistant from all three vertices. In other words, if you wanted to create or place a cell tower between three cities so that each city would get an equivalent signal strength, you could find that location using this method. The altitude is going to be a perpendicular segment from a vertex to the opposite base. So if I construct that perpendicular, so here's my right angle. That's my altitude. And when you're dealing with the altitudes, if you have an obtuse triangle, you would need to extend your sides. So I'm just going to make this an acute triangle here. And when I construct my perpendicular, okay, the intersection of those gives me my orthocenter. Okay, and so again, I'll kind of adjust this so I can make my markings. Okay, and so if I take this point and this side and find the perpendicular, it should pass through that exact same orthocenter point, which it does. So that verifies what I have here is my orthocenter. And like I said, there's nothing else that we're going to be doing with this other than identifying that this is connected to the point of concurrency of all three altitudes. That is the centroid. The centroid is the intersection of all three medians. Okay, and once again, a median, that is defined as the segment connecting a midpoint to the opposite vertex. And so we're going to take a look at both what this looks like as well as some special properties that exist regarding the centroid and the medians. So if we take this triangle to start with, to find the median, what we need is we need to find the midpoints of each side. So if we construct our midpoints first, so there's our midpoints. That means that these two sides are equal. These two sides are equal, and these two segments are equal. Okay, so there's the representation of our midpoints. And then if we connect those midpoints to the opposite vertex, that gives us our median. So if I connect the midpoint to the opposite vertex, that gives me my median. The intersection of my medians is going to be my centroid, so I can go ahead and label this even after 2. So there's my centroid, and if I wanted to verify it, I can construct my final one, the midpoint to the opposite vertex, construct that, and it passes through the exact same point. Okay. What you see here is that just like with the angle bisectors, the centroid is going to stay in the interior of the triangle. And in fact, the centroid is sort of the balance point of the triangle. If you had any object that was shaped like a triangle and you identified the centroid, that would be the point on which the center of gravity, or the point where that triangle would balance. So you could cut out a triangular figure, find the centroid, and that's where you could balance it on a pencil or on your finger. All right. Now, in addition to it being that center of gravity, and the other thing that a centroid does is it cuts the median into 2 parts with a ratio of 2 to 1. Okay, so the other thing that it's going to do is it cuts the median into a ratio of 2 to 1. And we can see that here with this measurement tool. Okay, if I were to find this length here, so if I were to measure that distance, so that's in this 1.75 centimeters, that means that this upper portion, the portion between the centroid and the vertex, is going to be double that. Okay, and so it's off by scales, but because it's rounding. But here you can see 1.81 is the distance from E to the centroid, and then the distance from the centroid to F is double that. Okay, and so you can think of this in terms of here in this triangle. If you connect each of these midpoints to find the centroid, one way that you could think of that is this distance, the distance between the midpoint and the centroid of X is half that, or is half that of the other distance, or the other distance is twice that of X. So you get this relationship. Okay, but using what we know about ratios, what if we were given the side, or the length between the vertex and the centroid? If we were told that this is Y, then what would this smaller portion be if it's a 2 to 1 ratio? It's 1/2 of that, right? So this could be 1/2 Y. And then the other way that you can think of this is, what if you were given this entire segment? If you were given the entire median length as Z, then we can split this into a ratio of 2 to 1. Well, if you were to compare each of these parts to the whole, you have a part-to-part ratio of 2 to 1, giving you a total sum of how many parts? 3. So this becomes 2/3 and 1/3. So the smaller piece is going to be 1/3 of Z. The longer piece is going to be twice that, or 2/3 of Z. And so there's these 3 different relationships, ways that you might look at these medians. It all depends on what you start with. Do you start with the small part and double it? Do you start with the big part and halve it? Or do you start with the whole and cut it into 1/3 of that and 2/3 of that? Okay, so let's take a look again at what the typical questions might look like.